Okay, so here we're going to take a look at representing functions as power series. All right, now a good starting point is our geometric function here. All right, because it represents this function. It's a good one to, at least when we have rational functions, to kind of see if I can represent it in some form or another with this power series. All right, so here my goal is going to be, excuse me. So in this example, I want to express 1 over 1 plus x squared as the sum of a power series. As the sum of a power series. And find the interval of convergence. Okay. So again, starting here, and really what it comes down to is just matching a pattern here. All right, so this is 1. I can think of this as 1 minus negative x squared. All right, and now it looks like this. So I can write it as negative x squared to the n is equal to 0. All right, and here writing it in the power series form. All right, I can have this as n is equal to 0 to infinity, negative 1 to the n of x to the 2n, right? Okay, so here what we have is what this looks like is 1 minus x squared plus x to the 4th, right, with only the even values, minus x to the 6th, etc., plus x to the 8th. Okay, and the interval convergence here will be the same. It would be from negative 1 to 1. Okay, and again, that you can find using, really here, we can see that this absolute value of x squared has to be less than 1, right? And we can go from there. Okay, but again, I'll skip all that just so as, we can just use the previous results known here. All right, and if we test the endpoints, you'll find out that they actually diverge at the endpoints, so we're left with that. And now, graphically, what you can see here, right, so what you see graphed here is 1 over 1 plus x squared. That's this black dotted line here. And the orange one is our power series, right, the sum of a power series, right, here where it's just the 0th term, so just one term. And as we let it sum more and more terms, we get a better and better approximation. Okay. All right, so now we have a way of approximating these functions using polynomials. Okay. All right, let's do one more example here. So how about here? So the same idea here. For this example, I want to express x cubed over x plus 2 as the sum of a power series and find the interval of convergence. Okay, so we'll start again trying to pattern match here. So we have, x cubed over, and I'll write it as 2 plus x. So I'm going to write this x cubed, and from the bottom, I'm going to factor out a 2. So 1 over 1 plus x over 2. Okay, and again, I just want to match it up with my geometric that I have up here. 1 minus negative x over 2. Okay. All right, and here, now I can use my power series from here, right, where here we'll have x cubed over 2 times the sum here of negative x over 2 to the n. Okay, and from here, writing it in power series form, I can rewrite this as x cubed over 2, again from n equals 0 to infinity. Here we go, let's see, so negative 1 to the n, here x to the n, over, oh sorry, sum n equals 0 to infinity, 2 to the n. Okay, and now here, looking at this, right, for our power series, you know that this, right, we know that has to be true, so what that leads us is that our interval convergence is going to be from negative 2 to 2. Okay, all right, more on that in a second here. Let me just keep simplifying here. So now this becomes, since I know this is, I'm only dealing with convergent values, I can actually just distribute these x cubed in the sum. So that becomes here the sum n equals to 0 to infinity, x cubed, x to the n, we get x to the n plus 3, and then 2 to the n plus 1. Okay, all right, and then here, right, we have our power series that looks like this, and we could see here, since where I got this from is our original geometric series, is that in order for this geometric power series to converge, that has to be less than 1. Doing simplification here, we have our interval to be between negative 2 and 2. All right, you can test the endpoints out, but you'll see that it'll be a divergent sequence at both the endpoints there. Okay, and then just so looking at the graph so we could see what it's representing here. So looking at our graph here, we get x cubed over, what was it, x plus 2? All right, and then here, negative n plus 2 to the n plus 1. All right, and now we can see here, started at 0 here, right? Even right away, it starts as a cubic, right? So it doesn't have the constant term here. So, and again, going more and more approximations, we see that we get closer and closer, and again, it expands more across that whole interval, right? From negative 2 to 2, right? It starts to get closer and closer to the actual function itself.